Before we look at how to use spherical coordinates to evaluate triple integrals with, let's have a review of spherical coordinates. We basically have a point in 3 space, which we can call point P, and the coordinates of P as spherical coordinates are rho, theta, and phi. If we drop a perpendicular from point P onto the xy plane, then the angle theta is measured clockwise from the positive x-axis. The distance of P from the origin is called rho, and the angle that OP makes with the positive z-axis clockwise is called phi. Then the relationship between rectangular and spherical coordinates are as follows. X is equal to rho sine phi cos theta, y is rho sine phi sine theta, and z is rho cos phi. Then we also have that x squared plus y squared plus z squared equals rho squared. Also note that rho is a length and hence can either be 0 or positive, but can't be negative. Then phi extends by definition from the positive z-axis to the negative z-axis, in other words from 0 to pi. We can now express a triple integral over the solid region E in terms of spherical coordinates as follows. It's a triple integral where phi goes from C to D, theta goes from alpha to beta, and rho goes from A to B. Note that we've replaced x, y, and z here with the corresponding spherical coordinates. Then we also always have a magic factor here, which is rho squared sine phi, which is basically the Jacobian for spherical coordinates. Here E is a spherical wedge defined as follows. The set of all triples phi, theta, or rather rho, theta, and phi, where rho is between A and B, theta is between alpha and beta, and phi is between C and D. We can also extend this definition to a more general spherical region. We can also have rho bound by two functions, g1 and g2, both functions of theta and phi. Before we look at the first example, I just want to add that using spherical coordinates to evaluate triple integrals with is particularly useful when the region of integration have boundaries that are spheres or cones. Let's look at this example. We have to evaluate this triple integral over the region B, where B is the unit ball defined by this set, all triples x, y, z, in other words rectangular coordinates, such that x squared plus y squared plus z squared is less than or equal to 1. This, of course, is the equation of a sphere, and hence we're going to use spherical coordinates to evaluate this triple integral with. So let's look at that. First, I'd like to look at the sketch for B. So it's basically just a sphere centered at the origin with radius 1. Now we can define B in terms of spherical coordinates. So it's all triples rho, theta, phi, such that, now looking at rho extends from the origin to the boundary of the solid. And it's clear here that rho must be between 0 and 1 then. Then theta is defined in the same way as it is for polar and cylindrical coordinates. Of course, it's the angle measured clockwise from the positive x-axis in the plane, the xy plane. And it's clear that since we're dealing with a sphere, theta extends right around, in other words, from 0 to 2 pi. Then remember that phi is the angle that the line segment, this line segment extending from the origin to the boundary of the solid, makes with a positive z-axis. And once again, since we're dealing with a sphere, we can see that phi extends from the positive z-axis right down to the negative z-axis. In other words, phi will be bound by 0 and of course pi. Now we're ready to set up the triple integral in cylindrical coordinates. So this will equal the triple integral of E. Now, x squared plus y squared plus z squared is rho squared in spherical coordinates. So rho squared to the power of 3 over 2 will just be rho cubed. Then we need the magic factor of rho squared sine phi. In other words, the Jacobian. And now we can put in the limits of integration. So we see that phi goes from 0 to pi. Of course, our order of integration will be d rho, d theta, d phi. Then theta, we said, goes from 0 to 2 pi. And rho goes from 0 to 1. And we can now evaluate this integral, this triple integral. Let's now continue evaluating this integral. We can pull out the sine phi and associate it with this integral from 0 to pi. Next we go to theta. Now there's no factor in theta in this expression, so it's just going to be 1 d theta or d theta. And then lastly, rho goes from 0 to 1, and we have rho squared e to the rho cubed, d rho. Then the antiderivative of sine phi is negative cos phi. From 0 to pi. And then the antiderivative of 1 d theta, of course, is just theta. And plugging in the top limit for theta, we're going to get 2 pi and then minus 0. So it's just 2 pi. Here we can use substitution. And we find that this is a third e to the rho cubed, evaluated from 0 to 1. Then the cos of pi, of course, is negative 1, and the cos of 0 is 1. We can plug in 1 for rho, so it's just going to be e to the 1. And in plugging in 0 for rho, we're going to get e to the 0, which is 1. Now we just simplify. It's going to be negative 2 times minus will give me plus 2. Times 2 is 4. So it's going to be 4 pi by 3 into e minus 1. Let's look at the second example on spherical coordinates. It says, use spherical coordinates to find the volume of the solid that lies above the cone. An equation of the cone is given here. And below the sphere with this equation. And then we are also given the diagram. We can perhaps start by writing the equation of the sphere in spherical coordinates. We know that x squared plus y squared plus z squared is rho squared. So we have rho squared equals z, which is rho cos phi. And we can solve this equation. So rho squared minus rho cos phi is 0. We can take out rho. Of course, rho is not 0, so we find that rho equals cos phi. So this is the equation of this particular sphere. Now we can go to the cone and write it in terms of spherical coordinates. We know that z is rho cos phi. So we have rho cos phi equals the square root of x squared plus y squared. And we can write in the spherical coordinates. So x squared is rho squared sine phi, or sine squared phi, cos squared theta. And of course y, or y squared, will be rho squared sine squared phi times sine squared theta. We can simplify this. We can pull out rho squared sine squared phi from under the square root. And what we have left underneath the square root will be cos squared theta plus sine squared theta, which of course is 1. Once again, we can solve this equation. Then we can take out the rho. And we find that cos phi equals sine phi, or sine phi equals cos phi. And in dividing through by cos phi, we get that tan phi equals 1, and hence phi will equal pi by 4. And this is in fact the equation of the cone in spherical coordinates. So we have both the equations of the sphere as well as the equation of, so this is the sphere, as well as the equation of the cone expressed in terms of spherical coordinates. We can now express the solid region E in terms of spherical coordinates. Now, we were told it's a region above the cone, but below the sphere. So this purple area here, or region, let's write E in terms of spherical coordinates. So E is the set of all triples, rho, theta, phi, such that, now looking at the rho is extending from 0 to the sphere, the top part of the sphere here. And we know the equation of the sphere is cos phi, rho equals cos phi. So rho will be between 0 and cos phi. Then theta goes from 0 to 2 pi. And in phi extends from the positive z-axis down to this part of the cone. In other words, phi will then be between 0 and pi by 4. We can now set up the triple integral. Now first note that the volume of a solid, in this case the volume of the solid E, is given by the triple integral over the solid E of 1 dV. In other words, just dV. We want to write this now in spherical coordinates. So theta goes from 0 to 2 pi. Phi goes from 0 to 4 or pi by 4. And rho goes from 0 to cos phi. And we have 1 dV. So we need the Jacobian in here for spherical coordinates, which of course is rho squared sine phi. And the order of integration here, of course, is d rho, then d phi, and then d theta. There's no theta in here, so it's just going to be d theta. Looking at phi, we have sine phi. And then we're going to have rho squared, which we can integrate as rho cubed over 3, evaluated from 0 to cos phi. And of course, we still need the d phi. Of course, this is just going to be theta, and we plug in 2 pi. We can also pull out a third right in front. And then plugging in cos phi for rho cubed will give us cos cubed phi. And plugging in 0 will give us 0. So we have 2 pi by 3, and we can use a substitution for this integral. We can let u equal cos phi, and then when we integrate that, we'll get negative cos to the 4 phi divided by 4, and this is evaluated from 0 to pi by 4. And our final answer comes to pi by 8.